我是统知3亿的林子轩。
Today, I'm going to present my final data mining report, focusing on the classification and clustering of arbitrary routing based on spatial features. To ensure my analytical pipeline, I established a robust programming environment by importing essential data science libraries. With my environment set, I ingested my primary data source, the Taipei City garbage collection rules and stubs datasets, sourced directly from the government open data platform. Before making any analytical assumption, I conducted a rigorous structural verification of my dataset. I inspected the exact dimensions, confirming I had successfully loaded 4,007 operation records distributed across 12 initial variables. I verified the data types to separate the continuous spatial coordinates from the category text loss. My primary research goal was defined to predict the operation shift, whether a stop belongs to the afternoon or evening shift. Based purely on this spatial and operational feature, building upon this foundation understanding, I transitioned into data preprocessing. During my recent vary detection, I identified a null record within the spatial coordinates. Because downstream algorithms rely strictly on equal distances, I completely dropped this invariant to prevent mathematical failure. I also applied one-hot according to my nominal features, such as district and routes, to prevent overlay bias. For my continuous coordinate, I applied the standard scalar to normalize the distance, preventing variables with larger numerous from dominating my models. I dropped several invariant discrete to reduce dimension and prevent future noise. Through this rigorous cleaning and encoding process, I successfully transformed a purely discrete dataset into a structured framework perfectly suited for machine learning. Entering my supervised learning phase, a major challenge was that the original dataset lacked a predicted touch variable. To resolve this, I applied discretization to the continuous arrival time feature. I utilized pandas to bring these continuous hours into distinct categorical operation shifts. I then deployed a label encoder to transform these text-based labels into a binary, machine-readable format, establishing the exact targeting label for my classifier to predict. With my features and target exactly, I executed a critical output step, splitting the data into an 80% training set and a 20% testing set. It is essential to emphasize that I perform this splitting before any feature scaling. This strict secrecy completely eliminated the risk of data leakage. I established my baseline using a distinction tree. As you can see in my overfitting analysis plot, the initial complete models yield strong training accuracy but suffer a drop in testing performance, a classic example of overfitting. To build a more recent models, I evaluate different features and method. I compare a tree unity of my engineered variable against one field by chi-square statistics. The result was defined. The model retained all variables, drastically outperforming the feature selection model, achieving an 89.01 test accuracy. I concluded that dropping variable prematurely discarded vital non-level spatial interactions. Therefore, my final recommend tree retains all features, but I successfully maintained the previous overfitting by carrying the maximum depth to 8. This resulted in an extreme compatibility of just 41 nodes. By decoding this tree, I extracted transparent wet box business rules, discovering that specific discrete numbers fundamentally dictating the evening shift, regardless of geographic variables. I abandoned this structure integrity using 5-fold cross-validation, achieving a high stable mean accuracy over 19% with minimal deviation, providing universal applicability. Transition to my second model, the support vector machine. I rely heavily on my strictly standardized dataset and one-hot encoding feature. I ensured the send scalar was fitted exclusively on the training state to prevent any data leakage before transforming the testset. My baseline SVM achieved over 19% accuracy right out of the box, confirming the effectiveness of my standardization strategy. I then conducted a high-parameter experiment comparing the linear kernel against the nonlinear RBF kernel across extremity planar values. This revealed a profound geometric insight. My one-hot encoding process embedding the routing data into a high-length space. High-dimensional space were data points on naturally linear variable. Consequently, the linear ZVM encoding made a perfectly stable hyperlink, maintaining an unwavering 92.02% testing accuracy. I highly recommend the linear SVM C01 for its parametric immunity and communication efficiency. My third architecture was the random forest. Unlike the SVM, I strictly avoid discrete and bypass the standard scalar, feeding the algorithm my raw continuous variable to preserve maximum numerical resolution. This baseline approach immediately dimensions expression predicting power. I then conduct an extensive turning comparison across 4 distinct settings to optimize the forest. I observed the various trade of the set, while setting the depth to understated achieve a massive 94% accuracy. It showed tendency of memory training noise. I ultimately select setting 4, a control architecture comparison 300 estimated with a streaming depth of 15. This model achieved a testing accuracy over 85.27%. The macro gaps of 0.09% from its training accuracy mathematically perfect generously with 0 overfitting. For my final dimension algorithm, I deploy k-nearest neighbors, returning to my strictly standardized dataset. My baseline KNN mapped the spatial features successfully but showed minor sensitivity to local noise. Requiring k-merit optimization, I iterated search for the optimal k-variant, as shown in my plot. The mathematical sweet spot was exactly k equal 1. By testing range from 1 to 20, k equal 1 consistently returned the highest testing accuracy, while k equal 1 often implies overfitting in standard table data. It is the absolute ultimate choice for highly precise GPS routing. The schedule at any given location is best predicted by the exact course's history stop, expanding the neighbor count artificial processing spatial noise from untrue routes. To bring my supervised learning to its ultimate conclusion, I construct voting classifiers. I unify the distinct strengths of my disease tree SVM, random forest, and KNN models. I evaluated both hard voting based on visual rules and soft voting, which averaging the underlying problem confidence. Comparing all 5 methodologies side by side reveals my definitive results. The soft voting classifier emerged as my understanding champion, reaching a peak testing accuracy of 94.51% by dynamically averaging the confidence. It neutralized the algorithm blind spot, perfectly synthesized the distance-based geometry of SVN and KNN with a rule-based library of my tree algorithms. In the final phase of my project, I pivoted to unsupervised learning to blindly discover hidden geometry patterns. Using the Albert method, I determined a baseline up to K of 4. I then advanced to a feature argument space by including my TLG variable. Instead of relying solely on visual inflection, I mathematically set this addition K to 2 to estimate the true output classes. Comparing these two structures, expanding K from 2 to 4 resulting in the marginal 0.79% reduction in spatial variance. I finalized my solution at K equal 4. Piloting the operation granularity required to manage distinct CT quadrants over purely mathematical boundaries. My serial team analysis returned negative scores, rather than an error. This perfectly reflects the reality of urban routing. Garbage trucks do not operate in isolated bubbles. The routes heavily overlap on shared arterial roads. When I provide these 4 final clusters, I made my most critical business discovery. The arrogant nature isolated class 1 and another long exhibit an impartial average longer of 164.87. By mathematically correcting these extreme GPS recording errors, K-means successfully protect the geographic interior of my variables. I transfer this portfolio into action levels. The central course spatial outliers, northern fast track, and eastern extending hub. Finally, I performed a cross-evaluation using a majority voting protocol, operating entirely blind to the true operational answers. My pure spatial K equal 4 model successfully reconstructed 75.56% of the human design dispatch network based solely on equidistance. This proves that Taipei's current rules are heavily grounded in geographic logic. In conclusion, my analytical result indicated that the soft voting classifier is the absolutely best model for this dataset. I have successfully transformed raw geographic coordinates into an intelligent, highly accurate, and deployed urban dispatching framework. Thank you very much.